The second major method of searching for exoplanets is called the transit method. A transit is a passing across. And in this method, astronomers rely on photometry. Remember, metry is measurement, photo is light. So this is the measurement of the amount of light that comes from a star. And it produces what's called a light curve. And so I've done this animation here to show you that if you turn a photometer onto this star, a certain amount of light will be coming from that star. And here's our planet that is orbiting this star, and it's not in front of it. But as soon as it starts to pass in front of that star, or transit to go across, the little shadow there is going to cause some of that light to be blocked. And on the light curve, that will show up as a drop in the amount of light coming from the star. That lower amount of light will stay steady as the planet completes its transit. And when it moves out from in front of that star, then the light curve will rise back up and it will continue. And then, of course, as the planet orbits and it begins this again, you'll see that same pattern of diminishing light and rising light repeating. And you can tell the orbital period of the planet, how long it takes to go around the star, by how long it takes to see this drop and rise in light.
Kepler infers the existence of planets by measuring the brightnesses of stars very, very precisely, searching for the telltale dimming of light that happens when a planet in its orbit about the star happens to pass directly between the disk of the star and the telescope itself.
Now remember, of course, that these stars are very far away, so they're much smaller than you saw in that animation. And the planet, of course, is even smaller compared to the star. So the drop in light is very, very small and has to be measured very, very carefully. That means, of course, that we have to try to eliminate the interference of Earth's atmosphere. And so to really search for exoplanets using the transit method, we put telescopes into orbit. And the very first space telescope that was developed was called Kepler, the first one that was designed specifically to look for exoplanets was called the Kepler mission. It ran from 2009 to 2018.
0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Before the launch of Kepler, most of the planets we knew about were really big planets like Jupiter. But Kepler was so sensitive that we started finding smaller and smaller planets.
We discovered planets smaller than had ever been discovered before, and just many of them, indicating that the galaxy's full of planets. Crazy worlds that we didn't predict, things that we hadn't imagined. We find planets orbiting so close to their parent star that the star-facing side has temperatures in excess of that required to melt iron. These planets have an entire hemisphere that's like a liquid ocean, but it's not an ocean of water, it's an ocean of molten rock. We see planets that are orbiting not one, but two stars. That is, if you look in the east, you'd see not one star rise, but two.
Almost all the astronomers that I know grew up reading science fiction. That's why a lot of them got into the business of looking for planets in the first place, to find out if any of this, fantastic speculation that inspired us could be true. And now we find out that, yeah, it could be true.
The Kepler mission ended in 2018, and that same year we launched another space telescope specifically designed to search for extrasolar planets. It's called TESS, for the Transiting Exoplanet Survey Satellite.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
During its 2-year survey, TESS will look for signs of planets, ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky, called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky.
So we have some incredible tools today for looking for exoplanets, and in the last video we'll look at some of the results of these planetary surveys.